Okay, good afternoon, everyone. So today we're going to talk about how we implement all these neural network things in PyTorch. So we're going to go through the code that is responsible for the demo that we saw in the beginning of this unit where we had the green and the blue points. So as we talked about last time, there's a few different ways to implement these neural networks using different software frameworks. Of the top three, we're going to focus on PyTorch because it's, in some sense, I wouldn't say it's the simplest. Keras is the simplest, but Keras is almost too simple in that it can't really do very much, not very flexible. It's hard to debug. So we're going to do PyTorch, simpler than TensorFlow, and probably the most popular model right now in the research and academic fields. So to do all this in PyTorch, there are quite a number of steps, and we're going to go through them. There's basically a recipe, and I would say that using an example is a good way to get started. So you have examples. I'm giving you, demo code that's an example. So if you ever want to do something similar later, you can just sort of modify those examples. You can find other examples online as well. Eventually, once you're expert enough, you could perhaps write the code from scratch. But basically, there's 5 steps. Constructing the data set and the data loader, constructing the network, selecting the optimizer and the loss, fitting the network parameters, and finally applying the network, which includes things like maybe extracting parameters, trained parameters from the network, and so on. Okay, and there's really good tutorials here if you ever want to take a look. But anyway, just going through our demo. First step, constructing the data set and data loader objects. Okay, so first we're going to import Torch. Torch is the library of PyTorch. It's not called PyTorch, it's called Torch for some reason. And within Torch, we need to get some utilities. And so the very first thing we're doing here is I think somewhere earlier in the code, we generated the data set. So we have a NumPy matrix X, which is going to have 2 columns, because we have 2 features, X0, X1, and a whole bunch of rows, and the rows correspond to the different training samples. And then we have a scalar binary label Y. So Y is just going to be a one-dimensional array in NumPy. And so the very first thing we need to do is we need to convert them to Torch tensors. So Torch tensor is very similar to a NumPy ND array. It works, it has most of the same features. However, it has a bunch of other things under the hood, such as connecting that variable to a computation graph, storing the gradient. So there's all this other stuff that it makes it very different from just a regular NumPy variable. But anyway, the first step is to bring these into PyTorch by recasting X and Y as Torch tensors, and we'll call them Xtorch, Ytorch. Now that we have that data set, we call this command tensor data set with those things, and we call the result this data set object. And this object is really going to hold all our training data. This has taken those Torch tensors and has added a lot of other bells and whistles to it to make this data set object. Now, if we want to do things like batch sampling, multiprocessor support, and by multiprocessor support, I mean sometimes when you have very big training sets, they don't even fit on a single machine. So you actually have them distributed across machines. Or when you're training, maybe the model is too big to fit on a given machine, so you split it across machines. And you need ways to move the data across machines. And so those are the things that are handled in this data loader. For us, we're not doing any of that multiprocessor stuff, but we do want to use random sampling, batch sampling. And so that's why we put the data set through this data loader object, and we'll call the result the loader. So to give you a sneak peek into how you could draw batches of data, it would just be these lines. So here you have a for loop for batch, comma, data in enumerate loader. So that would be the for loop that goes and draws batches. And then the batch would be in this data object, but this data object is going to contain both the features and the targets. So you just split them out this way. Okay, so every time you go through this loop here, this is going to draw new batch elements out of the loader, which contains your data set. And the loop will stop running once it has gone through the data completely and there's no more batches to draw because you've used all the samples in the data set. Okay, so that's how we're going to draw mini batches. Okay, so that's step one. Any questions here? All right, step two, construct the network. So in this case, we need to use the neural network library of PyTorch. So this knows about all kinds of different activation functions and linear layers and all kinds of other stuff that we haven't talked about yet. And so we're going to build an object, a class. So this is that object-oriented kind of framework here, where we need to have this function here, this is the function that is run automatically when you instantiate the object, and this does the initialization stuff. So here's the instantiation command. When we first create an instance of this thing called model, we have to tell it how many inputs, so this is like the number of features, the number of hidden nodes, and the number of output nodes. And so this is the function that takes in those three things, and then it creates a bunch of stuff and stores it internally as part of the model. So one of the things it does is it will create an activation function. Well, we're just calling it self.activation, and we're setting that as neural network.sigmoid. So now whenever you use this activation thing, it's essentially going to be a sigmoid. Of course, you could replace this with like ReLU, and then it would use one of those, or TANH. So we're just going to use a sigmoid here. Then we're going to, we have two linear layers, if you remember. There's like, the input goes in, there's a linear layer, there's activation functions, and then there's another linear layer, and there's one final, there's four of these in the middle. And there's one final one. So this is sort of how our network looks. And so each of these activations is going to be a sigmoid, and we're going to call this first linear layer dense, and we're going to call the second one, or dense 1 and dense 2. They are called dense layers because another very popular way to implement a linear layer that we'll talk about next unit is a convolutional layer. So if you have ever taken 3050 or 5200, you know that you can make a convolution matrix as a Toeplitz matrix. And so in that case, when you create a convolutional layer, instead of just a matrix where all the different elements could be anything you like, it's going to have that Toeplitz structure. It's going to be forced to have that convolution structure. And so, when you create these linear layers that have no structure, people often just refer to them as dense layers. So that's why we're calling it dense. But this is in the neural network library of PyTorch, it's linear, and you have to tell it how many inputs and how many outputs. So we'd have 2 inputs and 4 outputs the way we did the demo. Okay, so this is just setting up things in the neural network. And then this is defining the forward pass, or most of the forward pass. I guess we're not yet computing the loss, but we're taking this in and we're saying what are all the things that we need to do to compute the output of the neural network. So here you can see that we take in X, and we take X, we put it through dense 1, then the output of that we put through the activations. So that's going to give us this over here. We're just rewriting that as X, so we're not going to create a new variable just for efficiency. We'll overwrite the same variable. And then we'll take X, put it through dense 2, here, put it through the activation here, and then finally that gives us out and we'll return out. Okay, so that describes the forward processing of our neural network. Okay, so now we have our network made. Any questions on this? Okay. All right, so next we have to select the optimizer, the algorithm that we're going to use to optimize the weights and the loss that we want to minimize, the function. So we need to use torch.optim. That's the library that knows about all the different algorithms. And the most popular algorithm that people seem to use these days is called Atom. And so that's the one we're going to use. So you can see optim.atom. Now, when you instantiate this optimizer object, you have to tell Atom what are the parameters that you want it to optimize. And here you're saying you can find them in model.parameters. So again, model was this thing over here that contains our neural network. And so this just knows that the parameters to optimize are the things in linear. And then you also give it any kind of parameters, algorithmic parameters that you want. So the most important one will be the learning rate. So here we're saying use a learning rate of 0.01. But there's other parameters associated with Atom and other optimizers. Atom has a whole bunch of different parameters you can tweak if you want. And if you don't want to say what they are, then the default values will be used. So we'll just use the defaults except for the learning rate. So now we have our optimizer object. Now separately, we need to define what criteria we're using. So in other words, there's a criteria here that computes the loss as a function of the training labels, Y, and the network outputs, which I think we're calling AO in this demo, output activations. So this criteria we need to define. And so for classification, common things are binary cross-entropy loss or cross-entropy loss. For regression, popular things are MSE loss, which basically does RSS, or L1 loss, which has an absolute value instead of a square. So we're going to use binary cross-entropy loss. And I'll talk a little bit more about that in a few slides as to why we're using exactly that loss. But I think you remember that we are using essentially, we're thinking of this last layer as logistic regression. And logistic regression minimizes binary cross-entropy loss. At least the name makes sense. Another thing that's interesting about these losses is that you can do things like scale and combine them. PyTorch allows you to do that. So if you had two losses, like you define MSE loss and then you define L1 loss, you can actually write an algebraic expression like this, and it will know to scale one loss and to add it to another loss. So you can do things like that. Okay, so now we have our optimizer and loss set up. Any questions? Okay. All right, so now this is the more complicated slide, which shows us how we're going to put all these things together in order to train the network. So, so let's just start at the top. So first of all, we're saying how many epochs we're going to use for training. We'll use 2,000 epochs. This print interval is something that we will use. I guess I don't even think we're using it on this slide, but it's something that I think maybe somewhere else in the code will print something out every 100 epochs instead of printing things out every epoch, which would make a very long list of print statements. And then we're just initializing some quantities, some NumPy quantities, average loss, average accuracy, which we'll use to record the loss across the epochs and record the accuracy of the outputs across the epochs. Okay, so this is how we're going to do the training. So we have two loops nested. So we have an outer loop, which goes over the epochs. And we have an inner loop, which goes over the mini batches. For each epoch, we do all this mini batch stuff. So at the beginning of each epoch iteration, we zero some counters. So one of them is going to be our error counter. This is just going to count for all the samples in the epoch. It's going to count how many of them we're making an error on in our binary prediction, and the total counter is just going to count how many samples that we have in our epoch. How many samples basically in our training data set. And the batch loss is going to be a vector that will grow, that will keep adding the loss for each batch to it. And so we're just going to zero that out, make it an empty vector. Okay, so now we're ready to go to our inner loop. So in our inner loop, we essentially draw a mini batch from the data loader. So the mini batch is going to be in data. Then we're going to split out the features and the labels in our mini batch. Now, if you remember, the features that's a two-dimensional structure because it's a matrix of size number of samples in the batch by 2 because we have 2 features. Whereas Y batch is going to be a one-dimensional array, which is just the binary numbers in the batch. And the trouble is if you try to use that one-dimensional quantity later, I think in this criterion function, you would find that there's a mismatch in sizes. So this out will be a two-dimensional quantity. Even it will look like a column vector, but a column vector is a two-dimensional quantity that has a one column. Whereas this, as originally created, would be a one-dimensional quantity, and it would throw an error. It would say like they don't match. So what we have to do is we just have to reformat Y batch. Instead of a one-dimensional quantity, we're going to make it a two-dimensional quantity, which is basically like a column vector or a row vector. I guess a column vector that is going to have, it's a two-dimensional quantity with one column. And this view minus 1, 1 basically just says, think of the last dimension should have size 1. And so based on the number of elements in Y batch and the first dimension, it will figure out how to reshape it or resize it. So it resizes it to something of this shape. Okay. Is that pretty clear? Okay. So now we have our batch loaded and shaped in the right way. And so we can put our features through our model. This does the part of the forward pass that generates the output of the network. We'll call the output of the network out. So that's the output of the network for all the samples in the mini batch. And then we can measure our loss by putting out and Y batch through our criterion. So that's going to measure the binary cross entropy loss, which is just going to be a scalar quantity for that mini batch. We're then going to append that number to the batch loss vector, which starts as this empty vector and then just grows as we go through this, as we go round and around this inner loop. I think the loss has a bunch of other stuff in it. So if you want to actually extract the number, the value of the loss, you have to do dot item. Okay. So now we've computed our loss. Now that's essentially the forward pass. Forward pass is done. Now we do the backward pass. So the first thing we're going to do is we're going to zero the gradient in the optimizer. If you don't zero it, the gradient that you compute with backpropagation will just add to the previous gradient. And so you don't want that. You just want to zero it first. Then, when you do loss dot backward, that does all the complicated stuff that we discussed in the last 2 lectures. So it goes backwards through the computation graph, computes all the gradients, all that stuff is done, and it's all stored internally. All those gradients are actually stored as part of the variables themselves because these torch tensors, as I said, there's a lot of stuff under the hood that says what their values are, what their gradients are, how they're connected to the rest of the variables through the computation graph. So all that is sort of done in the background. Now that the gradients are computed, we can take an optimization step. And so you do that simply by doing optimizer.step. And then that will, if it was just simple gradient descent, it would take your old optimizer parameters plus the step size times the gradients to get the new ones, or minus the step size times gradient. If it's Atom, it's going to do a bunch of other complicated stuff. There's some variation on stochastic gradient descent. So after you do this, now your parameters are updated, and they're ready to do the next iteration. Okay, so now the last things we're going to do are just figure out how well our current outputs, how good they are. So first we can round the outputs because we're doing binary classification. Round will just turn them into a 0 or a 1. And so our guesses are now binary. And we can do guess minus y batch to, so if this number is 0, then that means that they agree. If this number is either 1 or minus 1, it means that there's an error. And so when you look at the absolute value of that, it's going to either be 0 if they agree or 1 if they don't agree. And we're just going to sum them across the batch and add that to the error variable. So now error will increase by the number of errors, binary errors in that batch. Meanwhile, the total will increase by the length of y batch. Okay. And so now we've finished processing that batch. Now we go to the next batch, and we repeat this process again. Draw on new samples, do the forward pass, zero the gradients, do the backward pass, compute the new loss on the batch, the new errors on the batch, and so on. And we just do this over and over and over, and eventually this loop will stop once you've gone through all the data. And then you'll come down to here. So this is now at the end of the epoch. We can compute the accuracy for that epoch. So you do 100 because we're going to do percent, 1 minus error over total. So that will be the accuracy for that epoch. And we'll store that accuracy here in the average accuracy vector. And then for the loss, we've computed the batch loss. So this is going to be, let's see. I guess maybe this is, yes, okay. So the batch loss, for every batch, it's a scalar. But what we did is as we went through this epoch, we just made this vector batch loss longer and longer. It contained the losses for every batch in the epoch. And now we just want to average those losses over the entire epoch. So we're doing mean here. And that will be the average loss of all the batches in that epoch. Okay. So we've computed all these things, and I'll show you plots. We'll plot these things in the next few pages, and you'll see how they look over the epochs. Okay, so this is the hardest slide. It has really all this stuff going on, but this is kind of how things look in PyTorch. It's how you do things in PyTorch. Okay. Any questions on this procedure? Okay. All right, great. So let's take a look at the performance versus epoch. So here we're plotting versus epochs. This is the loss. So you can see the loss started out high. Very quickly, it came down, but then somewhat more slowly, and then even more slowly here over these 2,000 iterations. The training accuracy went up to about 70, then kind of stalled for a while, and then went up to almost, but not quite 90%. And this is what happens over the epochs. This curve looks nice and smooth. If you looked at what happens within an epoch, it would look very noisy. Across the batches, the loss would be going like up and down. But once you average over the epoch, things are much more smooth. Okay. All right. Yes?
Sorry, just to make sure I'm interpreting that correctly. is that a very nearly vertical slope at like 0 to maybe like 5 or something? Or is that a perfectly vertical line?
It's very nearly vertical.
Okay, just wanted to make sure there wasn't some weird misunderstanding.
Yeah. Yeah, I don't know exactly at what point it jumps down to 0.6, but it's pretty quick. Okay. All right. Any other questions? Okay. So, all right. So that was kind of the hard part, training the network. So now I'll describe a few other things, such as how we created this plot. So here, the thing I'm going to focus on is this shaded red region. How do we create that? So essentially, to do that, we created a very dense grid in this two-dimensional domain. So to create that grid, okay, first we said, okay, we want x, want the minimum x values down here to be 0 and 0, the maximum x values to be 1 and 1. And then we made a one-dimensional grid in the x0 along this direction. And that one-dimensional grid was a Lin space starting at 0, ending at 1, with 100 points. So we made a one-dimensional grid along x0. Then we made a one-dimensional grid along x1. And then there's this command mesh grid that you may have seen before, maybe in MATLAB even, because they have exactly the same command. Mesh grid is a nice way of taking two one-dimensional grids and creating a two-dimensional grid from them. So what it does is you give it the two 1D grids, which are these ones, and it basically gives you a matrix of the x0 numbers as you go through this bigger grid. So it's a matrix of just the x0s and then another matrix of just the x1s. And then what we really need to give our neural network is we need to make a very tall matrix that's going to have two columns, because our features, we always have two features, and it's going to have 100 squared rows, right? Because there's 100 points along each grid. So it's 100 squared 2D points. So to create that 100 squared by 2 vector, we do column stack. We do ravel on this first matrix, which strings out that matrix into a big long vector. And we do ravel on the second one. Now that's a big long vector of x1s. Do column stack to make it a matrix with two columns. And that's our xplot matrix. That's sort of like, you could say it's a big test matrix of all these different test points that we want to test our network at. So they're basically doing that with mesh grid. Now that we have created xplot, this is something that we created in NumPy. So in order to actually use it with our PyTorch stuff, we have to cast it as a torch tensor. So we get xplot tensor. Now we can put it through our model. And our model will give us out another torch tensor. And that torch tensor, as we said, has all this other stuff attached to it. It knows about the computation graph, gradients, all this stuff. And so we don't want all that. We just want it for plotting purposes. So we use .detach to detach it from the computation graph, so it's just some numbers. And then we said recast it as NumPy. So now we turn it into a NumPy array and an ND array. And this is finally something we can work with in NumPy, like we can use standard like reshape commands, or we can plot it, all those things. So that's essentially, here we basically have to convert to PyTorch, do PyTorch processing, and then convert back to NumPy, and then you can use it in NumPy. And what we're doing in this line is just reshaping. This is going to be one big long vector that has all these outputs in it. And we're just now reshaping that as a matrix, 100 by 100 matrix that we can use for plotting. So we have to do just a little bit more pre-processing. So the matrix that we constructed, actually the origin is up here. That's 0, 0. So for this command to plot it, we want the the origin to be down here, so we do flip UD, which flips the matrix up and down. And then we just do im show, which is how we plot images. And so we get this nice plot here. There's probably some other parameters in there. Maybe not. Okay. And then to get the color bar, you just do PLT color bar, and that adds that. And then the last thing we're doing is we're just going to overlay these blue and green samples down here. So we're just plotting them as blue and green dots, basically, and adding the labels and title. Okay, so that's how we got that. So detached NumPy is kind of the main thing we learned here. Okay, any questions? Okay, good. So another thing we did in the demo is we created these plots that were showing what happens at the hidden layer of the network. So the next question, well, how do you extract that information? Because our network, that kind of model function just gives you the output. So what if you want something inside? So for this, you can actually just manually piece together the processing you want using the structures inside the model. So we're going to take our XPlot tensor, and first we're going to put it through model.dense1, which was that first linear stage. Then we're going to take the result and put it through model.activation, because those are the two steps we need to get to the hidden activations. So here we're just manually creating those hidden activations using those two model processing steps. That's going to be a torch tensor. So we detach it to NumPy, and now we're going to reshape this thing into a 3D tensor. It's the first two dimensions are nplot, which are basically those two dimensions, and the fourth dimension of this tensor is across the number of hidden channels. We had 4 hidden channels, so it's sort of like those 4 things. So that's this new thing we created here. Now, if you notice in the titles, I'm actually plotting the values of the weights in the output layer. So how do you get those numbers? Okay, so that is where this model state dictionary comes in. So the state dictionary is what you use when you want to extract the weights. The state dictionary here that we created actually has like all the different parameters in it. So we want to say, okay, let's look at the state dictionary, let's look at the weights of the dense 2 layer. So we're going to put those in WO, and then the dense 2 bias, we'll put those in BO. So now we have those numbers, and somewhere here in the title of those plots, you can see we're putting in the values that came out of here. Okay, so yeah, those are the main things on this slide. Any questions there? Okay. All right, so that was just the demo. So with a very small change in the code, we can apply this to MNIST. Really all we need to do, we're going to use exactly the same architecture and everything. We just need to change the number of hidden nodes to a larger number, because 4 hidden nodes is not really enough for MNIST. MNIST is more complicated, so we're going to use 100. You could play with different numbers to see how that affects things. And because in MNIST we're doing classification with 10 different classes, we need to have 10 output nodes, right? So we're going to use 10 output nodes. Also, although I didn't mention it here, we don't want to put the outputs through a sigmoid, because a sigmoid would only be appropriate for binary classification. I believe that in this demo we probably didn't have any output activation. We just had the 10 scores at the output of the 10 output layer scores be the final outputs of the network. When we train, we need to use cross entropy loss, because we're doing classification with more than 2 classes. We have a choice over the hidden activation functions. We'll use sigmoidal again. They seem to work okay. We'll use the same optimizer, Atom, but this time we'll decrease the learning rate by a factor of 10. And we'll use 50,000 training samples and 10,000 test samples. So it's not common when you work with deep networks to do k-fold cross-validation. This is the simplest form of cross-validation where you have a fixed training set, fixed test set. You train on the train set and you test on the test set, and that's all. And you can do cross-validation. It's just more expensive. Training even one of these models might take a little while depending on the hardware you're using. So cross-validation would probably be, it would be nice, but it's just too expensive. Okay, so this is what we get as you go through the epochs. You can see the training accuracy. This is actually only over 30 epochs. This is probably how many I used. Training accuracy is going up, getting close to 100%. That's not too surprising, actually. When you work with neural networks, especially if you have a neural network that is very sophisticated, it has a lot of, let's say, a lot of nodes, a lot of power to learn functions. It can, what we call, memorize the training set. It can basically learn all about that training set. That does not mean it's a great predictor. It just means it's really kind of memorized the training set. So it's very typical to see the accuracy go up and possibly hit 100. That's not something you should be very excited about because that doesn't mean your test accuracy is going to be 100%. So when we look at our test accuracy, we see that is coming up to somewhere, around between 96 and 98. So somewhere like above 97. That's pretty good, right? That was what we got with the support vector machine with the radial basis function kernel. It was also 97, I think 97.0.1, something like that. So actually, this very simple 2-layer neural network, it works quite well. If we want to make a direct comparison to the support vector machine, it's a little complicated. So one thing we can say for certain is that when you use this neural network for classification, so not training, but just what we call inference or the testing phase, it's way faster because all you have to do is you have to take an image and you just push it through basically like a matrix multiply, a few scalar nonlinearities, another matrix multiply, and that's it. It's incredibly fast. If you want to use a support vector machine for inference, remember you have to use all the support vectors. You have to basically do inner products with them inside this kernel function. And so if you have a lot of support vectors, then it takes a long time just to make a single prediction on one single test sample. So you would find that this neural network is way faster for inference than a support vector machine. Now, in terms of training time, I'm not sure which one is going to be faster. It's going to depend quite a bit on the hardware you use. If you have a GPU, that is going to speed up things dramatically for the neural networks. GPU, scikit-learn has some GPU acceleration for some of their functions, but it doesn't work nearly as well as GPU acceleration does in PyTorch for deep networks. So it might help a little bit, but I'm not sure. It's a little bit hard to do a comparison. The other thing about the support vector machine is that, roughly speaking, the complexity grows quadratically with the training size. And it also is a function of how many support vectors. So if you have a few support vectors, the support vector machine runs faster. But remember that the number of support vectors is something we need to choose with cross-validation. So that's also going to be part of our, I don't know. Maybe we shouldn't consider that part of the training. It's more part of like the optimization of the approach. Because here if you want to do this optimization of this neural network, you would probably have to do something where you play around with different numbers of hidden nodes until you're happy. Maybe you would play around with other things like the activation function, the step size, and so on. I'll talk about that in just a moment, the different things we need to tweak. But overall, at the end of the day, test accuracy is similar to the support vector machine. We could probably do better than this even, but this is quite good. Okay, so any questions on this? Yes?
Would you do even better if you added just another hidden layer?
Yeah, definitely. It's hard to say because at some point, once your network gets too complicated, you might find that it starts overfitting in a way that it just has too many parameters to learn for the size of your data set. So it's really tough to say exactly how many layers is going to be optimal. I suspect that 3 is going to be better than 2, but is 10 going to be better than 3? Maybe not. So this is the sort of thing on the final project. When you do it, I'll just be giving you a data set, and whoever's doing the neural network will just have to try things and gain some experience in how these things behave. Yeah.
So is there like a rule of thumb used on like how many like nodes you should give like the dimension of the size of your data set?
Not really. It really depends on a lot of things, just the properties of the data set. So, yeah, it's unfortunately, yeah, there's no real like common rules of thumb. There are some like different strategies, like one of the trouble when you have to choose all these parameters, you don't want your search space to be massive. So like if, let's say you want to have, 10 layers, rather than individually optimizing the number of hidden nodes at every layer, which is going to be 10 different numbers or 9 different numbers, maybe you just make them all equal and then you just optimize that single number. That's a lot more manageable than trying to tweak 10 numbers. Or sometimes people do something, they'll have the first hidden layer have the most parameters and then it will like decrease as they go. Or sometimes they'll have it start small, go big, and small again. And I don't think any of those are necessarily better than others. It just really depends on the data, which one will work better. But those are a few things that people do to make it manageable to design these. Okay, great. Okay, any other questions for now? Okay. All right, so let's talk more about like the decisions to make when we do this stuff. And this is just going to be for the 2-layer neural network. Okay, so a very important thing we have to choose is how many hidden units do we use? We used 100 there. Maybe 200 would have worked better. Maybe 50 would have worked better. Who knows? You got to try different things. The type of hidden layer activation functions. So we use sigmoid. We could have used tanh or ReLU, other things. Then there's the optimizer. Which optimizer do we use? We used Atom, but there's a bunch of other ones. There's the learning rate. This is a pretty important decision to make. We'll talk a little bit more about this in the next unit, but because this is not convex optimization, if you use a really small learning rate, what will happen, or what often happens, is you start randomly and then you end up trapped in just the nearest local minima. If you use a bigger learning rate, it will actually bounce you out of bad local minima, which tend to be sort of shallow and wide, and then it will bounce you into a deeper global minima, and you will tend to stay there. So getting the learning rate right is not just a matter of speed, how fast you converge, but it's actually a matter of where you converge to. In convex optimization, the learning rate just needs to be small enough that you get to the global minima. Making it larger just makes it faster up to a point where it may not converge. But here it's actually quite different. Another strategy is to actually change the learning rate over the epochs. It's called scheduling. So often what people use is a large initial learning rate followed by a smaller final learning rate. The large one hopefully bounces you out of the bad local minima. The small one later prevents you from bouncing around too much in a good global minima. because if your learning rate is big, you'll just bounce around the bottom and you'll never settle. So making it small eventually will help you settle down. So that's probably the most common schedule, but there's many other schedules where you start small, get big, go small, and kind of alternate between them. Sometimes there's like a cosine thing where you go up and down and up and down. There's all sorts of different schedules, and it's not clear which one is the best. Another consideration is the batch size. Sometimes this is limited by the amount of memory you have. Like if you're working with large images, you simply can't store that many large images in your GPU's RAM, so that will control how big of a batch you can use. But like for a toy problem like this, we could have used a very big batch. Memory is not an issue. But we talked before about trade-offs with batch size and the advantages of stochastic gradient descent over plane gradient descent. So I think if the batch size got too big, I think it just wouldn't be as efficient. So there's going to be sort of an optimum batch size. And that, again, is something that there's no great rule of thumb. It's maybe, you just try a few values, see if you can find a good one. The number of epochs is maybe a bit of an easier decision. As you can see here, things seem to be getting better as we go. So if we would have only used, let's say, 5 epochs, we would have definitely not had the best performance possible. So by using more epochs, seems like things are getting better. At some point, maybe if you would have gone to 100, you would have seen that not much is really changing. Now, there are other things you can do. So you might actually believe, for example, that the model at 27, which has what looks to be the highest validation accuracy, you might believe that that's actually the best model. So what you might do is you might, as you're going through the epochs, you might store the weights every epoch, and then just store the weights of the best network you've seen so far. So every time you have a new best, you store those weights. And so when you're all done, you would look back and say, okay, this was my best one, so I'm going to use those weights. Now, those were the best on this this test set. But if you have another test set, like maybe you're doing some competition and the competition held out another test set, it does not mean that what you saw as best on your test set is going to match their test set or their validation set. And in fact, the more you do this, the more you run experiments with your test set and tweak things until your test accuracy is optimized, the more you will overfit to your test set. And the farther the worse it will work on, the held out validation set that they're using to score the contest. So there's sort of a bit of a danger in terms of overusing test. If you really do it to an extreme, you could almost say that your test is actually being used as training data set, right? Not really used as test, it's used just as training in some sense. So you have to be a bit careful in not overusing your test set. Otherwise, you just can't really trust the results you get. Okay. All right, so that's the number of epochs. There's a bunch of other tricks. L2 regularization is a trick that that actually works really well in neural networks. It works well for a complicated reason and not an intuitive reason, but it actually helps make the network weights sparser in the way that lasso for typical things like logistic regression. Well, it turns out that for these neural networks, L2 regularization actually makes the weights sparser because of the nonlinearities in the network. And so that has a nice quality of reducing the number of weights that are actually learned, and it can help with performance. Turns out that the way to do this is super easy. In the optimizer, there's an option in all these optimizers called weight decay, and actually in that case, even the bias coefficients, they're also regularized. So all those coefficients are just regularized by some value, some weight that you specify there. So it's super easy to do. You can try different weight decays, do grid search, do cross-validation, so on. Okay. So as you can see, there's, even for a 2-layer neural network, there's quite a lot of decisions to make, quite a lot of things to try if you really want to optimize this. And you can do this all by hand. Another option is there are packages. These are what we call hyperparameters. The parameters of the networks are like the thetas, like the weights and the biases. All of these things are called hyperparameters. There are hyperparameter tuning packages. Optuna is one of the nicest ones. And what it does is it automates all this for you. You tell it, like, these are all the things I want to tune. These are the ranges I want to tune them in. And it doesn't just do a massive grid search, because a massive grid search, if you have 10 parameters, your grid would be of like some size to the power 10. So that, you know, the grid size grows exponentially in the number of things you're tuning. So instead of doing that, it does something more intelligent where it randomly tries a bunch of different settings for these hyperparameters. And for the ones that seem like they're better, it does random variations on them. So in a very sophisticated way, it focuses in on the ones that seem to be working well, and it still does a bit of exploration around them. And it tries to, in minimum time, really test out all the possibilities. So what I've seen in all the projects for previous semesters of this course, that the manual tuning method works about equally to this Optuna method. So, and what I mean by that is Optuna takes a long time, because if you really say, try all these parameters, like, you might have to let it run for a week or something. And then after a week, like, if something is not quite right, then you have to go back and do it again. So it just takes forever. Now, if you're, a clever student and you sort of understand, or you just try things and you start to see patterns, you can become a very sophisticated tuner yourself. And I find that works just as well as Optuna. Like, I don't really see Optuna beating the students that tune things themselves. I've never seen that. Like, in the best case, they're pretty similar. Okay, so there's several options there in terms of how you decide on all these different things here. Okay. All right. Any questions on that? All right. It's getting close to the end here. All right. Last slide is just sort of a little bit of a warning on how you choose your loss. So, and I mentioned this before too, but the idea is that when you define the cross-entropy loss, for example, there's a couple different ways to define it. One way to define it uses the output scores, the Z's. Another way to define it is in terms of the output activations, where these activations are the outputs of the sigmoid fed by Z. So these are mathematically equivalent. They're identical. Both of them work, I would say, equally well in terms of training your network. But it's critical that when you construct your network, or when you use this loss, that you really do feed it Z. If you instead fed this loss with the output of a sigmoid activation, it would no longer be right, and it would not work. I mean, it would work maybe a little bit, but it wouldn't work well. Similarly, if you used this loss, but you fed it Z, it wouldn't work. Okay, so it's just, you have to make sure that however you construct your network, that you're using the appropriate loss. So now, in terms of PyTorch, if you're doing binary classification, you have two choices. BCE with Logit's loss takes the Z's as the input. On the other hand, BCE loss takes the activations A as the input. Okay, so you're free to construct your network either way, but if you construct your network that outputs Z, you must use this. On the other hand, if you construct your network so that it outputs A, you must use this. You don't want to mix it. Now, if we're doing more than two classes, we can use cross-entropy loss. That takes these logits, that vector of scores. On the other hand, if you want to put those scores through a softmax to get these these A's, then you have to use this NLL loss. Okay, so again, you just have to use the right one. This blog post talks about this in a little bit more detail, but this is the basic message. So PyTorch gives you options. You just have to make sure you use them correctly. Okay, and with that, you have everything you need to know about this unit, about these MLPs, multi-layer perceptrons, or two-layer neural networks. So there's a midterm coming 2 weeks from today, Wednesday, not Friday, because 2 weeks from today on Friday is no class. So 2 weeks from today on Wednesday, we're going to have a midterm. The midterm will cover up to including this unit. Nothing on the next unit, Unit 9. Okay, so this is the end of the material for the midterm. So on Friday, I will post homework for this. So you'll have, have a week to do the homework, and then the midterm will be the following week. That following week, of course, you won't have any other homework. Just, I should say that the week when you study for the midterm, you won't have any homework. You'll just, I'll post a practice exam again. If I have time, I'll even post a few more practice things for the midterm. Okay, any questions about next midterm? Yeah.
It's 5, 6, 7, 8 sections.
Yes, it will focus on units 5, 6, 7, and 8. Now, there is some material in 5, 6, 7, and 8 that builds on the earlier, but yeah, I'm not going to specifically try to ask you on details in the earlier things, but focus on classification, optimization, SVM, neural networks, shallow networks. Okay, now, looking forward in the course, Unit 9, the next one, is going to be on deep networks, convolutional networks. That will be the last unit where you have a homework and a lab. After that, there will be no more homeworks and labs. You'll have time to work on your project. Okay, so units 8 and 9 are the last homeworks and labs. You will have quizzes on the remaining units, but no more homework and lab after Unit 9. The project, I still need to put the project details together. The project, you'll be given a data set, and you'll be given a task, like this is, binary classification. And you won't really know anything else about the data set. And so you'll just be using the techniques that we learned in this course to try to do that classification or regression, whichever one it is, as well as possible. So in a 3-person team, the kind of techniques we're looking at are what I would call the linear techniques, which is like logistic regression if we're talking about classification. Logistic regression, SVM, then neural networks, and then something we'll talk about in Unit 10, which is ensemble methods, trees. So in these 3-people teams, it often works well to have one person do the linear stuff, one person do the neural networks, one person do the trees. It's just a nice way to split it up. It doesn't have to be that way. And if you get along with your teammates, you can work together with them. You can all collaborate on all the methods. If you don't get along with your teammates, that's fine. You can just split up the work, just need to agree on that, and then do the work separately. And at the end of the day, you just need to merge your project reports into one PDF on Carmen. When I grade it, I will grade, everybody needs to tell me what you did, what you wrote, and what you coded. And based on that, I'll give you individual grades. Okay, so whether you want to work with your teammates or not, it's up to you. Okay, so that's kind of just a preview of the rest of the course. Are there any questions, high-level questions about any of this? Okay, and then finally, the final project is due just near just before finals week starts, right around that time. So it's before finals week, just at the end of the class session. Okay, so that's it. All right, see you guys on Friday.